All right, so in the first chapter, chapter one, the introduction to this course, I would like to go over basic definitions and basic formulas that are very important, and they define the elements, the basic elements that we use in circuits, the current, the voltage, and other quantities that we always calculate when we analyze an electric circuit. We always try to find the current, the voltage, the charge, the flow of the charge, and other things that we must be familiar with before we go into an advanced and talk about advanced methods of circuit analysis. We need to know the foundation and the definition of these terms. So I'm going to start with number one, charge and current. So if we take a basic electric circuits, you will see these elements in the circuit. You will see a voltage source, a battery, of course. You will see wires, and there's a switch, for example, here. And then you will see, maybe this is a very basic circuit, maybe you will see a resistor in the circuit. So what happens is that when we close the switch at specific time, charge electrons will flow from the source through the resistor and will complete the path through this resistor back to the source. We have a closed circuit, and these electrons will flow from the negative terminal of the source to the positive in this direction. So this flow of charge in the circuit can be represented by the current. The current in the circuit usually is defined, the direction of the current is always defined as opposite to the direction of the flow of the electrons. So I, the current, is the time rate of change of charge. Mathematically, I is dq dt. Q is charge, and it's measured in coulombs. C, coulombs. And time is measured in seconds. So 1 amp is 1 coulomb per second. The units we use for the current is amps, coulomb, second. So 1 amp is 1 coulomb per second. One coulomb is 6.25 times 10 to the 18 electrons. Or you can say 1 electron has a charge that is 1.6 times 10 to the negative 19 coulomb. So 1 coulomb is a large quantity. It's a large quantity. So usually charge, when we talk about charge, maybe it's in millicoulomb, microcoulomb, and so on. Or the current, maybe milliamp or microamp. So we will use smaller units than amps and coulombs. All right. So this is our first equation defining the current as the rate of change, the time rate of change of charge.
Dr. Chiave?
Yes, Luis.
The book has 6.24.
The book has what?
For electrons, right? You put 6.25 times 10 to the 18th.
Oh, yes. Thank you. Let me fix that. Good. All right. So that's the relation between the current and the charge. Also, we can rewrite this relation. We can say that charge Q is the integral of current. So either this integral relation or this derivative relation. So whatever you have, let's say, for example, you want to find the current. If you're given the charge, then you differentiate. So here, we'll give you an example. The charge entering a terminal is given by the equation Q is 5t sine 4 pi t, and the units millicoulomb. Find the current when t is 0.5 seconds. So all I need to do to find the current is take the derivative of the expression of the charge, dq dt. So d dt 5t sine 4 pi t. And that we have two terms here, the 5t and the sine 4 pi t. So we're going to use a product rule for differentiating. So the derivative of the first, 5t times sine 4 pi t plus 5t times the derivative of sine 4 pi t. So we have 5 sine 4 pi t plus the derivative of sine 4 pi t, the derivative of the inside is 4 pi times 5t, so that's 20 pi t. And then derivative of sine is cosine 4 pi t. And the units now is milliamp. Because we started with millicoulombs, it is now current is milliamps. Now we want to evaluate the current when t is 0.5. So I 0.5, going to substitute 0.5 into t, so 5 sine 2 pi plus 20 pi times 0.5, so that's 10 pi, and then cosine 2 pi milliamps. So this part here is 0, cosine 2 pi is 1, so therefore 10 pi milliamp, or approximately 31.42 milliamp. Okay, so we took the derivative of the expression for the charge to get the current. In the other direction, if we have the current, or if you have the charge and you want to find the current, you need to integrate. So here's another example. Determine the total charge entering a terminal between t equals 1 second and t equals 2 seconds. And I'm going to give you the equation for the current. I is 3t squared minus 1 amp. Three t squared minus 1. So how do I find the charge from the current? I integrate. I'm going to say Q is the integral. Now, the limits of our integration is from 1 to 2, because we want to find the total charge going into that element within a specific period of time, within this period from 1 second to 2. So the integral from 1 to 2 of I dt. So Q integral from 1 to 2, 3t squared minus 1 dt. Integrate t cubed minus t. And then the integral from 1 to 2. So substitute the 2, the upper limit first. So 8 minus 2, that's 6. And then substitute 1, 0, 6 watt coulombs. All right, so 6 coulombs is the total charge entering the element or entering that terminal over this period of time between 1 and 2 seconds. Also, we're gonna find the charge from the current, but sometimes we have an initial charge, an initial value for the charge that we also need to consider. So for example, find the charge.
Dr. Chiave,
Yes.
your integral of 3t to the square minus t, I believe, right?
Uh-huh.
You put, isn't it t squared? 1/2?
No, it's 3t squared minus 1. It's not 3t squared minus t.
Okay.
Yeah, 3t squared minus 1.
Okay.
So find the charge Q of t flowing through a device if the current is, I'm going to give you the equation of the current, I of t is 3 e to the minus 5t. And let's say this is in milliamps. Also, I'm going to give you an initial value for the charge. Let's say the initial value for the charge is 1 millicoulomb. All right, so we want to find an expression for the charge based on the given expression for the current and the initial value of the charge. So again, we write our relation. Q is the integral of I dt. We need to integrate. So Q is the integral of 3 e to the minus 5t dt. We integrate. Integral of e to the minus 5t is e to the minus 5t over negative 5, right? Plus a constant of integration. So Q is negative 3 over 5 e to the minus 5t plus c. Now we need to find that constant of integration using the initial value that is given for us, Q of 0. Q of 0 is 1. So if I substitute 0 into t, that will give me negative 3 over 5 plus c, and that is equal to 1. So therefore, c is 8 over 5. So that's the constant. So now the expression for the charge is what? Negative 3 over 5 e to the minus 5t plus 8 over 5. And you can check, if you put 0 into t, you will get 1 for the charge. And this is, again, the units here, millicoulomb. All right, so that's the relation between current and charge. Also, a very important quantity that we will always be calculating in this course is the voltage across a specific circuit element, across an element. So let's define the voltage. Number 2. So for example, again, if you go back to our basic circuit, voltage source, battery, and let's say a resistor, again, one resistor here, R. Once you close the switch in the circuit, again, the current will flow through the resistor. So let's talk about, again, electrons will flow through the resistor. Now, to be able to go through the resistor, this charge, to be able to go through the resistor, it needs energy. So what are we going to notice here? That we're going to notice a difference in potential, or a voltage across the resistor, developed across the resistor. So if this, say, for example, here, this is node B or point B, and this is A, there is a voltage or a potential difference between these 2 points. We call it voltage, VAB. And VAB has a polarity. Each voltage across an element has a polarity. So positive, negative, right? The current or the electrons will flow. They need energy. They need energy to move through that element. There is a voltage that is going to develop across that element. We label it VAB, and that voltage has a polarity. The voltage at A is higher than the voltage at B, right? So later we're going to learn that the voltage VAB is going to be the same as the voltage across the battery, the voltage source. So in general, voltage is the energy required to move a unit charge from a reference point negative, the point that has a lower potential, lower voltage, negative, to another point positive, and that quantity is measured in volts. The voltage is measured in volts. So again, the definition, VAB, the voltage developed across the circuit element. VAB, A and B are the terminals of the element, is always equal to the dW over dQ. All right, the amount of energy divided by the charge moving through this element. Now, W is energy and is measured in joules. And Q is charge measured in coulombs. So 1 volt is equal to 1 joule per coulomb. That's the definition of 1 volt.
Professor Shabi, I have a couple questions.
Yes.
Okay, so on the diagram that you drew, is there only a voltage difference or a voltage because there's a resistor in between? So if it was just any other 2 points on one of the lines, would there be a voltage between them?
No, no. If there is no element, no resistor, or no circuit element or capacitor, we're going to talk about other circuit elements. If there is nothing there, then there is no voltage.
Okay.
The voltage exists only across the terminals of a circuit element. In this case, the resistor.
And then my other question was, so point A, we refer to it as positive. Is that because, okay, so even though the electrons are moving counterclockwise,
Yeah, so the electrons are moving now in circuit theory. The current, the direction of the current is always opposite to the movement or the flow of electrons. So the current in the circuit flows from the positive terminal of the battery through the resistor to the negative terminal, which is opposite to the flow of the electrons. That's
So-
called the passive sign convention.
the positive point or whatever would be on the side closest to where the current is flowing, I guess.
Exactly, yes. Current is entering the element. Usually it enters from the positive side of the element, of the resistor.
Okay. Thank you.
Yes. Mhm. So yes, in general, guys, later on, we're going to use the passive sign convention. We're not going to talk about flow of electrons anymore. I'm just here. I just wanted to explain the definition of the voltage. The voltage source, the battery in this case, is going to give us a current. The current is going to flow through the resistor. The current, when it flows through the resistor, it flows into the resistor from the positive terminal, of the resistor. So we have what we call a voltage across the resistor with this polarity, positive at A, negative at B. All right. So that's the definition of the voltage. The next thing I have is the definition of power. Each circuit element in any circuit, electric circuit, is going to either give us energy, produce energy, or absorbs energy. The element's going to either supply energy, like for example, in this simple circuit, the battery is supplying energy, enabling a current to flow through the circuit. But the resistor at the same time is absorbing power or absorbing energy. So we need to define power. Let's talk about power. Power is the time rate of expending or absorbing energy and is measured in watts. So it's the rate of change of energy, dWdt. Now I can use this definition to find a relation between power absorbed or supplied by the element and the voltage and the current, the voltage across the element and the current going through the element. So here we have a circuit element. I'm going to use this box here to represent a general circuit element. So we have, let's say this is current flowing here, and this is the voltage across the element. So in terms of I and V, I'm going to find a relation or find an equation to find the power that will give me the power in terms of the current going through the circuit element and the voltage across the circuit element. So we do it here. P is dW dQ, the rate of change of energy with respect to charge, times dQ dt, right? Instead of dW dt, the rate of change, the time rate of change of the energy, I can express this rate as the product of these two rates. But the first rate, the rate of energy with respect to charge, is the voltage across the element, right? And the time rate of charge, that's the current going through the element. So I come up with this very important relation. P is V times I. V is in volts again, volt. I is in amps, amp, and P is watts.
Dr. Chiave, I have
Yes.
a question. From a system standpoint, when you look at your electronic device, it says the number of watts. This is the same principle, but at the system level, is that correct?
From a system point of view, I'm sorry, what is it?
Like, I mean, your device, it says it takes 3 watts.
Yes. Mhm.
So you can use the same calculation to figure out how many amps it's drawing?
Correct. Yes. If you connect that device to a source, a voltage, whatever that voltage is, and you already know the power that is, absorbed by that device, divide the power by the voltage, you get the current that goes through that device. All right. So guys, notice here, my equation says the power absorbed or expended by any device, any element, depends on the current through the element and the voltage across the element. This power, this equation here, we have to be careful. This equation valid only, or this is VI, when you have a current flowing into the circuit element from the positive terminal, right? So the current flowing into the device or the element from the positive terminal of that device. Then the power is equal to V times I. Now, if we have a device like this one here, and this is the positive terminal, this is the negative terminal, and the current is flowing out of the positive, not going into, but flowing out of the positive terminal or flowing into the negative terminal, then the power in this case is what? Is negative. There's a negative sign here, VI. And negative power, when there is a negative sign here, that means the device or the element is supplying or generating power in the circuit, not absorbing. Like when you have a battery here, suppose we have a DC source and there's current coming out of the source, I, this is Vs. This element, this battery is supplying, providing power to the rest of the elements in the circuit. Okay, so the power of this battery is going to be negative. There's a negative sign, negative TV times I. Okay, the power of each circuit element in the circuit is going to be, if the other circuit elements are resistors, then the power of these resistors is going to be positive. And positive power must be equal to the negative power. The total, the sum of the power in the circuit must be 0. The sum of the total amount of power generated in the circuit must be equal to the total amount of power absorbed in the circuit. Right?
Dr. Chiave,
Yes.
sorry. I'm a little confused. Can you look at page, in the book, page 11?
11. Yes, what is it?
In the figure 1.8? Can you, I'm a little confused. So the arrow pointing towards the element itself is positive power. So what does that mean versus pointing the other way?
These are exactly what I have here. So you have in figure 1.8,
Array, yeah.
let me write it here, figure 1.8, you have an element, and this is the positive terminal, negative terminal. This is the voltage across the element, and the current is entering the element.
Okay.
Entering.
So this is the actual flow of the electrons from negative to positive. Is that correct?
No, I don't worry about the flow of electrons anymore. Just focus on the direction of the current in the circuit. The direction of the current is going into the circuit, into the element from the positive, from the higher voltage, the positive terminal of the element. So the
Okay.
power is going to be V times I.
Okay. So that's different to the battery. Is that correct?
Yeah, the battery is exactly the opposite. The battery gives you current, like what I did here.
Yeah. Okay.
Here's the battery, supplies, gives you current. The current comes out of the positive terminal, goes into the negative terminal. So in this case, the power is negative V times I
For the battery or for the element itself?
for the battery.
It's still negative,
Yeah, for the battery, it's negative.
going from positive to negative.
The current goes out of the positive into the negative. Yes,
It's still negative V times I.
yes.
Okay.
Yeah. Every time the L current goes into the negative terminal, comes out of the positive terminal, this element gives you energy. The power is negative. I'm going to give you an example. 1 second here. Let me find an example on this.
Professor, can you make these notes available? Your notes, can you upload them later on?
Yes, Kevin, they will be available right after the meeting. I'm going to post them in Canvas.
Thank you.
Yes. Here's an example on finding the power absorbed or supplied by each element. All right, so let's start with the voltage source here. DC voltage source, a battery is the voltage of the battery is 30 volts and is giving a current of 10 amps. What is the value of the power? P1, negative current is coming out of the positive terminal. So negative 30 volts times 10 amps. So negative 300 watts. That's P1. P2, which is the power absorbed by this element here. Notice how the current is going into the element, and look at the polarity of the voltage, positive. So it's going into the element from the positive side. So P2 is just V times I, which is 10 volts times 10 amps, 100 watts.
Dr. Shiabe, can you disregard the arrows and determine what's absorbing and what's generating in the diagram?
No, you have to look at the direction of the current. You cannot ignore that.
So the diagram says the current, well, okay,
You have to use the directions that are given.
okay, all right.
When you go to P3, the third element, again, look at the direction of the current. The current is going into the element on the positive side. Again, using the passive sign convention, the power is V times I, 20 volts times 14 amps. Positive.
Professor, quick question. The I equals 10A, is that the sum of the current for both sides, or is that only for the left side?
Yeah, the 10A is the current coming from the source. That's the current going into the element here. The current comes from the battery, from the source, goes into this element, 10 amps.
But only for the left side. So or is this for the entire circuit?
Well, this current is going to flow through this element and is going to branch out. Here there is a node, right? At the node, some of the current, there's a current here, 14 amps, that goes in here, and there's a current coming from this direction. At each node, whatever goes into the node, whatever current goes into the node will come out of the node. So don't worry about whether it's going for the entire circuit or not. Just look at the current going into the element itself.
Okay, thank you very much.
Okay. Okay.
And then, Professor, I have one more question.
Yes.
So on each of the elements, the positive and negative side, that's to let you know, which way the voltage difference is. If that makes sense, that's what tells us if the element is supplying power or if it's using power, basically.
Correct. Yes.
Okay, cool.
Yes. The sign of the power. So here, see how we got the negative? That means this element is supplying or generating power. The other one, P2 and P3, are positive. This is positive here. And the other one, 20 times 14, 280, also positive watts. That's also, this element is what absorbing.
Got it. Thank you.
Let's go to the next one. P4. Again, focus only on the polarity of the voltage and the current. Now, P4, if you look at the current, is going into the element from which side? From the negative side. So if I want to find the value of the power, I will say what? Negative the voltage is what? 8 volts times 4 amps. And that will give me negative 32 watts. And now we go to P5.
What kind of
Notice. Yes, Rainier, go ahead.
what kind of element is that? Why is it like a?
Yeah, so it looks different here because this is an element that gives you a current that depends on the current somewhere else in the circuit. This is called a dependent current source. The current that this element provides or gives in the circuit depends on a current flowing somewhere else in another part of the circuit. So this is called a dependent current source. Notice here how the current is 0.4 I. Okay. And notice how the current, the direction of the arrow, here how it goes from the negative to the positive, it leaves the element out of the positive terminal. So when I calculate the power, I'm going to put a negative sign. I'm going to say 12 volts and then times the current, which is 0.4 I. But what is I in this case? Where is I? I is right here, 10 amps. So the current coming from this source is 0.4 times the current coming from the battery. So 0.4 times 10.
So it's not always. It's not. Is it always gonna be the current that's provided by the battery, or in this case, it's just that I?
No, only in this case. It could be any current.
Got
It
it.
could be anything, yes. So that will give me negative 48 watts. All right. Now to check our work, the sum of all of these powers must be 0. Negative 300, positive 100, 280, positive, negative 32, negative 48. The total or the sum of all the powers in the circuit must be 0. Is it 0? Let's check it. Negative 300 plus 100 plus 280 minus 32 minus 48.
Professor?
Yes.
Sorry, one more question regarding P4.
Uh-huh.
Why does it go from negative to positive? Sorry about my alarm.
P4.
Yeah,
Yeah.
why is it negative to positive when the other side is positive to negative?
Okay, no problem. Look at the direction of the current. Look here, just focus here. The current goes into the element from the negative side. The current goes into the box from the negative polarity of the voltage. So it's hitting the negative side. So based on the convention that we're using, in this case, the power is going to be negative. And then whatever the voltage is, 8 volts, and then times the current.
Dr. Shiaba, you can say it's the same thing about the 30 volt P1 too, right? Because power is going into the negative terminal.
That's not quite my question though. I understand that you can basically just look at the symbol and then determine that it's negative that it'll be a negative power. My question is that let's just say they didn't physically put like the negative to positive sign. Is there a way for me to know, like by
No.
convention, that that should be negative to positive?
No, if they do not show you the negative positive, you can't tell.
Okay, thank you very much.
Yeah. You have to see, you will be given the polarity and the direction of the current, and based on that, you will be able to determine whether the power is negative or positive. Okay. So I'm checking, guys, negative 300 plus 100 plus 280 minus 32 minus 48. That would give me 0. So my numbers are good. The total sum of all the powers generated plus absorbed is 0.
Professor, I had a question.
Yes.
So for P5, if I went around to the other side, to the negative side of the element, would it be negative 10?
In P5,
Yeah,
the current is going into the negative.
right. The current is, but so it's negative 12V times 0.4 I. I is going through from the positive end. If it were to go in through the negative end, would it equal negative 10?
Yeah, don't worry about where it's going to.
Okay, so this one. Okay, so it doesn't really matter whether it goes in through the positive or negative side?
It doesn't matter what happens after. It is just the current, the magnitude of the current is 10 amps.
Okay.
So, yeah.
Gotcha. Thank you.
Dr. Chiave, so there should be an error going into the power supply, right, at P1 on the negative side?
Correct.
To
So
follow the convention.
the current is going to come back and enter the power supply from the negative and is going to leave from the positive.
Okay, I have another question on P5. How do you determine a dependent, I guess, is it current or voltage source?
No, it's a current source. You see, it's
Right, but it's 0.4 times 10. So
0.4 times 10. This is still current. This is current. It is just your scaling.
yeah, I'm sorry. Yeah, okay.
You still
But then you added the 10, right? They were all 10. Oh, I see what you're saying. I got it.
0.4 times 10.
Yeah.
4.
I got it. Okay, I is the 10.
Yeah.